theory, his theory of relativity, actually predicts that light will curve, and Newton predicts this as well. Newtonian physics predicts that light will curve, but if you do the Einsteinian calculation, the general relativity calculation, for reasons we'll talk about in a little bit, it's about twice as much. It's not exactly twice as much, and in fact, it wasn't really until very close to this confirmation that Einstein nailed down what it was, because the math is very, very difficult, and he kept making mistakes, and that's actually a very interesting story. But here's the picture, right? Here are three stars whose positions we know. We know where all the stars are. Any star you can see with the naked eye, we know where they are. We've got star charts, their exact positions, right? If you see these stars, though, close to a massive object, and the only object of decent mass that we have close to us is the sun, if we see that, right, then what's going to happen is the light is going to bend around it. And it's a bit like if somebody kneels on the golf green, which you're not supposed to do, but if you do, you leave this dent in it, yeah? And then whenever anybody's ball goes by that dent, what does it do? It doesn't go straight. It kind of curves around it and goes off like that, right? Okay. Well, here on Earth, if we're watching these stars, we're not going to look at that and go, oh, well, due to the curvature, our brain will automatically adjust or something like that. No. What happens is we assume light goes in a straight line, and we project the image of that star to be here. That's where we see it. It really is here, but we see it in the sky there. It shifts away from objects of mass. Isn't that weird? Right? It really is behind the sun, but we see it off to the side because of the curvature of actually space itself, right? Okay. Now, here's an interesting thing, right? In 1919, Sir Arthur Eddington, what country is he probably from? Yeah, he's from the UK. He's from England. I don't know, when did they call it the UK?
He's from the Navy.
After what?
After it was called England.
Yeah. You know, but anyway, Sir Arthur Eddington goes, so see, here's the problem, right? What's the problem with this observation? Why can't we normally see stars close to the sun? What's our normal problem with that? Have you ever seen any stars real close to the sun?
It's bright.
It's too bright, but you can sometimes see stars near the sun. It doesn't happen very often, but you can. Why? How? When there's a solar eclipse, when the moon, which very serendipitously happens to be almost exactly the same size as the sun in the sky. It's a smaller object, but much closer, right? It can actually block the sun, and you can only see the atmosphere of the sun, which is kind of a crazy thing, right? And apparently the sun gets so dark that you can see stars close to the sun. Now this only happens every so many years, and so and you can actually you can buy solar eclipse expeditions where cruise ships will follow and go out to where there's going to be a good solar eclipse, because oftentimes it only happens in the ocean, right? It'll cross the earth in some path like that, and you can get there and it can be cloudy. Isn't that sad? Spend thousands of dollars, like, right? Okay, so Sir Arthur Eddington goes there, and I believe there was some, the weather almost was bad, but wasn't bad. He confirms this, that the amount of bending was twice as much as what Newton predicted. This kind of confirmed Einstein's theory. We got better data later, but the interesting thing was that around this time, Einstein was famously Jewish, as I recall. Yes, okay, and around this time, right, wasn't Hitler starting to rise into power? Yeah? It was a little bit later, but they were confirming, basically the British were trying to confirm the Jewish science, right? Because Hitler actually had this campaign to discredit Einstein. Didn't work so well, right? It wasn't one of those best projects, right? But he actually had this campaign, and so the British are notably, right, that's the word I was looking for, notably doing things to confirm Einstein's theories, not just making up numbers to confirm them, but going out there and confirming them. And Hitler didn't like that, so that's kind of an interesting thing. There's a good story there. So if you need to do some report, if you're a political science person and you're taking like physics for poets or something like that in college, that's an interesting thing to look into, is the Jewish science that he tried to get rid of, right? So here's a picture. These are pictures of gravitational lensing, okay? And this is a wide field planetary camera. So it's just like an ordinary telescope on the Hubble, right? Visible light. And then if you look at this bright object here is a quasar. A quasar, as you recall, is a very massive object, like 30 to 70 to, I don't know, millions of stellar masses, of solar masses, right? Okay, so there's a quasar there. There's our massive object. Take a look at these guys here. See these guys sort of conspicuously smeared? If you look for it, you see little circles around it, right? Those are galaxies that are farther, that are behind that quasar. Their light is being pushed off to the side by the gravitational lens. You can also see something around this, right? Now the cool thing about this is that these lenses are magnifying lenses. And so we're seeing much larger and distorted. They're not, perfect, but really smart people can undistort that image. And we can look at galaxies farther away than we might by using gravitational lenses. There's a whole group of people doing this, right? But anyway, here's lensing there. Here is the famous Einstein cross, right? Why does it make 4? I don't know. Okay, I asked a theoretical physicist. I'm like, some guy had a PhD in theoretical physics, and I go like, oh, good. Explain this. He goes, I don't know, right? Because it's it involves 4-dimensional geometry, right? So not a whole lot of people understand general relativity. Okay, it's kind of one of those things, right? But sometimes it's 2, sometimes it's 4. Here's one that's way behind it that's smeared off there, right? So, now that I've convinced you that gravity bends light, the thing you need to understand is that gravity doesn't bend light. Light travels in a straight line. It's the space itself around a massive object that's warped by gravity. Yes? Okay. Light travels at the speed of light. It travels in a straight line, okay, at the speed of light. It's space itself that's warped. Yes? That could be, right? If I bend a piece of paper and then draw it, stretch a string like that, it'll appear to follow a curved path, right? But it's really traveling in a straight path. This is weird. So let's talk about dimensions. I think some kid in the first period lapsed into unconsciousness and like smoke came out of their ear or something like during this, right? So let's look. Here's a one-dimensional universe. Yes. Okay, we have only length. Okay, now if we take this one-dimensional universe, can't we bend it? But this requires at least, we need 2 dimensions to bend it. These are spatial dimensions. But these people cannot conceive of this other dimension. In fact, I can take this, and if I cut the string and join it, I could make a circle, couldn't I? This would be a one-dimensional object with uniform positive curvature, is what we say. It's got uniform positive curvature, and it's one-dimensional. This is a finite universe, that is, there's not an infinite amount of string here, and it's unbounded. In other words, if I actually cut it and joined it, right, it's unbounded, a finite, unbounded, one-dimensional universe. You could travel in any direction, and, well, you'd never run into a boundary, right? You'd never reach like an edge and go, oh, well, beyond that there's cheese, and then after that there's the peanut butter or something like that, right? Okay. This is, by the way, Keenan would, when he was like really young, like 8 years old, and I was tucking him into bed, he'd say, Dad, do you think the universe is finite and bounded, or finite and unbounded, right? Not that he understood this necessarily at age 8. He knew that if you started talking to Dad that way, what would Dad do? Yeah, Dad'd be like, well, that's an interesting question you got there, young man. Let's consider the possibilities of spatial curvature. Blah 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 blah. Like, yeah, I could stay up a little longer, right? There we have it. No, he understood it all. Okay. Right. So there's your one-dimensional universe. Shall we up the ante a little bit? Shall we? Let's go to a 2-dimensional universe. Now we've got length and width, but we have strangely nothing in this dimension. It's like we turn on edge, we're invisible. We're not like hard to see. We're just gone, right? We have no extent in the 3rd dimension. Yes. Okay. Now, this is a finite, bounded 2-dimensional universe of strangely rectangular dimensions, right? People on this universe might go, "Hey, this is just legal size, or not legal, but letter size paper." Okay. Thank you, Mary Grace. These are things. Official-looking things. Heaven the yay host, sitting alone at the front of the room with his red shorts on. Here we go. Okay, where were we? 2-dimensional universe. Are you picturing this? Okay. Now, can't we take this universe and we can have fun with this thing, can't we? Can't we bend it? But bending it requires 3 dimensions, 3 spatial dimensions. Can they picture this 3rd dimension? No, it is inconceivable to them. They cannot picture that. It's like, can't picture it, right? Okay. Now, even more interestingly, I can take this paper and I can go like that, can't I? And traveling around here, you could go around this loop and you could go across. If I just touch these guys together, it looks like it's very far from this point to this point, doesn't it? And you could disappear from this point and appear instantly at this point. It would be a great mystery, right? People in this thing would be like, I don't get it. right? How'd they do that, right?